Hey folks, continuing on here in Chapter 10. In Section 10.4, we're going to add 3 more weapons to our arsenal and how to attack infinite series. They are what your book calls the Divergence Test, and then the Integral Test, and special series called P-Series. So, as I said, in this section, we're going to learn 3 new weapons to add to our arsenal in analyzing series. Remember in the previous section, we learned about telescoping series and geometric series. With the telescoping series and geometric series, we could, fairly readily, we could determine the sum of a convergent series. So a telescoping series or a geometric series that converged, we had a way to determine the sum of the series. However, for most series that converge, it is difficult, extremely difficult, if not impossible for a lot, to determine the exact value of the sum. We'll see at the end of this section, we can come up with an approximation and a lower bound and an upper bound for an approximation if we so desire. Now remember in the last section, I did state that there were 2 big questions when dealing with infinite series. Question 1, does a series converge or diverge? Question 2, if it does converge, what is its sum? Well, because question 2 is, difficult if not impossible a lot of times, our focus is going to be more on answering the first question. Does a series converge or diverge? And if it does converge, as I just alluded to, it may be possible to estimate its sum. So the first new test that we're going to look at, it's a pretty simple one, yet it's a really powerful one. It goes by many different names. I'm probably going to refer to it more often than not as the first name, the Nth Term Test. The book calls it the Divergence Test. Some people call it the Nth Term Test for Divergence. And truth be told, the latter name, the Nth Term Test for Divergence, it may be the most descriptive for what it actually does. I see I have a typo there. So Nth Term Test for Divergence, that's pretty descriptive for what this test does. So I'll call it the Nth Term Test for Divergence here in this definition box. So here's the deal. If the series a sub n converges, then the limit as n goes to infinity of a sub n must equal 0. Likewise, if the limit as n goes to infinity of a sub n does not equal 0, then the series a sub n diverges. And that's where the power of the Nth Term Test for Divergence is if the limit as n goes to infinity of a sub n, remember a sub n is the kind of like the sequence that's determining the terms of the series. If it's not heading to 0, there is no way the series can converge. If it's not heading to 0, the series has to diverge. So something that I've alluded to, in the past, when you look at the terms of the series, it's, are the terms of the series approaching 0? And then are they approaching 0 rapidly? So it's absolutely necessary. It's a necessary condition for a series to converge that the limit of the terms have to be heading to 0. But that's not a sufficient condition. So I do want to, before I go any further, I do want to talk about what this Nth Term Test, it's the Nth Term Test for Divergence. It doesn't tell us, it cannot tell us if a series converges. In other words, if the limit as n goes to infinity of a sub n is 0, that does not mean the series converges. It just means the series is a candidate to converge. So make sure you understand the Nth Term Test. That's why I say I think calling it the Nth Term Test for Divergence is maybe the best name for it. because it's very descriptive. It tells you what it does. All right, so let's look at an example here. Do the following converge, diverge, or do we not know? And, we'll state a reason. So here are 3 series. So what, I'll ask you to do is, write these down in your notes because I'm going to head off to the chalkboard and work these out. All right, folks, here in our first example, we're asked to determine if the following series converge, diverge, or do we just not know? And then I also said to state a reason, trying to prep you for how one should answer these types of questions. So let's see, let's look at the first series here. N equals 1 to infinity, n over 2n plus 3. So when I look at this, I'm thinking something's kind of suspicious here. In other words, I'm thinking if we do the limit as n goes to infinity of n over 2n plus 3, well, we can divide everything in the numerator and everything in the denominator by n. So that gives us a 1 over 2 plus 3 over n. And this limit, well, the limit as n goes to infinity of 1 is 1. The limit as n goes to infinity of 2 is 2. And the limit as n goes to infinity of 3 over n, well, that's 0. So we get the limit to be 1/2. And we know 1/2 does not equal 0. So that tells us that our series diverges. It diverges because of the nth term test. Or as I named it in the slide, the nth term test for divergence. Because it only tells us when a series will diverge. So, in short, what it's saying is if you write down the terms of this series, if you keep going out farther and farther, the terms are not approaching 0. And if the terms of a series do not approach 0, there is no way the series can converge. In fact, not only do the terms of the series have to approach 0, but they have to approach 0 kind of rapidly. All right, let's look at the next one. Series from n equals 1 to infinity, 1 over n squared. So when I look at this one, the first thing that I at least notice right away is that limit is 0. All that tells me is that this series is a candidate to converge. So the series may or it may not converge. I don't know. It's inconclusive. The nth term test does not tell me anything about convergence of a series. Please remember that. You can never tell me a series converges because of the nth term test. It's the nth term test for divergence. All right, let's look at part C here. There's a lot going on here. I would say the first thing, well, let me write down trying to do this limit. Alright, so there's the limit. I have a negative exponent, so something's popping into my head here. Maybe I should rewrite this as 1 over n plus 1 over n to the nth power. That way I got rid of the negative exponent. And then look inside the parentheses. Inside the parentheses, I mean, I can clean this up. I could write it as n over n plus 1 over n. Well, n over n is 1 plus 1 over n to the nth power. And now I know exactly what this limit is. The limit as n goes to infinity of 1 is 1. The limit as n goes to infinity of 1 plus 1 over n to the nth power, that limit is e. And this does not equal, 1 over e does not equal 0. And because it doesn't equal 0, I know my series. The series n plus 1 over n to the negative n. I know it diverges thanks to the nth term test. So an old limit came back. That was important information for me to remember. So here's 3 examples where each one of them I kind of showed you the mechanics of the nth term test. You know, when the limit using the nth term test does not equal 0, you know the series diverges, as in A and C. If you look at the limit and you get a limit of 0, you know nothing. It's a candidate to converge. It may or may not converge. You don't know. So that's it for that example. So you know what? Let's head back to the slides and see what's next. All right, folks. I hope those examples made sense. Continuing on, you know, if you look at the series we've dealt with so far, our main focus has been on series that exclusively have positive terms. And we're going to continue just looking at series with positive terms for a little bit, this section and the next. But I'm just giving a heads up that it won't be too long, and we're going to be considering series that have negative terms as well. All right, hey, remember back in Calculus 1, the definite integral, the integral a to b f of x dx, you remember at its core, the definite integral was defined as being a, quote, limit of a sum. Logically, it seems reasonable that a definite integral can be used to determine if a sum has a limit. That is, we should be able to use an integral to tell us the convergence or divergence of a series. And that brings us to our next test. It's called the integral test. And here's the preamble to the integral test. If f is a function that is positive, continuous, and decreasing on the interval 1 to infinity, so that we're talking about a function of real numbers there, and if a sub n equals f of n, so your sequence agrees with the function of reals for all positive integers, then the series a sub n and the improper integral 1 to infinity f of x dx, they either both converge or they both diverge. So here's what's kind of cool. We're going to use an improper integral, see if an improper integral converges or diverges, and then that's going to tell us the behavior of the series. Quick note here, in this theorem, the number 1, it may be replaced by any positive integer. So you could replace the 1 with a 3. Again, this all goes back to the first few terms mean nothing for the long-term behavior if something converges or diverges. And then note number 2, if the improper integral converges, the value of the improper integral does not equal the sum of the series in general. So if we evaluate an improper integral and we get a number which tells us the improper integral converges, don't think that number is telling us the sum of the infinite series. It's not true in general. So let's look at an example here. Does the following series converge or diverge? By the way, the series I'm going to show you is called the Harmonic Series. Knowing the series by name and knowing its behavior, whether it converges or diverges, it's going to be extremely important. So there it is. That's the harmonic series. So I'm going to head off to the chalkboard, work this out to determine if this converges or diverges. All right, hey, this example, we're asked to determine if the series converges or diverges. This series has a name. It's called the Harmonic Series. I will need you to know this is the Harmonic Series. And once we crank through this example, we're going to know if the Harmonic Series converges or diverges. So that's going to be important information for you to know. All right, so I look at this series, and the first thing that pops into my head, well, actually the first thing that might pop into my head is, what's the limit as n goes to infinity of 1 over n? That limit is 0. That just means, hey, it's a candidate to converge. So then the next thing that pops into my head is, well, let's look at the function 1 over x on the interval 1 to infinity. So when you look at the preamble of the integral test, you have to look at this function and you have to satisfy 3 things about this function. Thing 1, is the function positive? On the interval 1 to infinity. Thing 2, is the function continuous on the interval 1 to infinity? Thing 3, is the function decreasing on the interval 1 to infinity? Yes, it's positive on the interval 1 to infinity. Yes, it is continuous on the interval 1 to infinity. Yes, it is decreasing on the interval 1 to infinity. I mean, I could quickly compute the derivative and see the derivative is always negative, or it's negative on the interval 1 to infinity. So, yes, it satisfies all 3 conditions. So because it satisfies all 3 conditions, I can use the integral test. So the integral test says we're going to analyze an improper integral. We're going to look at the integral from 1 to infinity, 1 over x dx. And it's the behavior of this improper integral. You know, the integral test says the improper integral and the infinite series, they either both converge or they both diverge. Well, let's analyze this. If this ends up converging, then we know that the harmonic series converges. If this diverges, then we know the harmonic series diverges. So let's attack this improper integral. Remember, you rewrite it. The limit as b goes to infinity. The integral 1 to b, 1 over x dx. And you get yourself an antiderivative. The antiderivative of 1 over x is the natural log of x. We're going to evaluate that from 1 to b. Notice I didn't put the x inside absolute values because we're only dealing with positive numbers here. So we have the limit as b goes to infinity, the natural log of b minus the natural log of 1. The natural log of 1, well, that's 0. The limit as b goes to infinity, natural log b, it's infinity. So that tells us, remember, this tells us that the improper integral diverges. Since we know the improper integral diverges, that tells us this series diverges thanks to the integral test. So now you know the harmonic series diverges. File that away. It's going to be important. When we start looking at other tests, like the direct comparison test or the limit comparison test, this will be important to know. You'll know right away, hey, harmonic series diverges. So file that away. And Hey, let's head back to the slides and see what's next. All right, hey, so now that we've seen the harmonic series, we know the harmonic series diverges. That's something you just need to know. File it away in the memory banks. It's going to be very useful in the future to just know that that series diverges. So let's do another example. Does the following series converge? The sum n equals 1 to infinity, 1 over n squared plus 1. So you know the drill. Make sure you have this written down because I'm going to head off to the chalkboard and work it out. All right, hey, I guess I wanted to do another example where maybe we'd be using the integral test. So let's look at this one. Does the series converge or diverge? And it's the series n equals 1 to infinity, 1 over n squared plus 1. So a very quick check. The limit as n goes to infinity of 1 over n squared plus 1. That limit is 0. I need to do some more work. This is still a candidate to converge. So I kind of quickly look at doing the nth term test. So what pops into my head, and this is just kind of something going forward, if I see something that I think, man, I can quickly and easily integrate that, that's a good candidate for the integral test. So what do I mean? If I look at the function 1 over x squared plus 1 on the interval 1 to infinity, and I make sure that that function is positive, continuous, and decreasing on that interval, I know I can quickly integrate this function of the reals. That means I should be able to crank this through the integral test. So continuing, we're going to integrate 1 to infinity, 1 over x squared plus 1 dx, which you know to rewrite as the limit as b goes to infinity, the integral 1 to b, 1 over x squared plus 1 dx. And like I said, that integral, that's an easy integral. 1 over x squared plus 1. That antiderivative is inverse tangent. So you have the limit as b goes to infinity of inverse tangent b minus inverse tangent of 1. And we know the inverse tangent of 1, we know inverse tangent of 1 is pi over 4. And thanks to the graph of inverse tangent, we know the limit as b goes to infinity, inverse tangent b. Thanks to the graph of inverse tangent, we know that limit is pi over 2. So this improper integral has a value of pi over 4. Because it has a value of pi over 4, that tells us that the improper integral converges, which tells us this series converges thanks to the integral test. And, one more time, folks, just because we have the value of the improper integral to be pi over 4, I've already mentioned this, I'm going to mention it again, that does not mean this series has a sum of pi over 4. That's not true in general. It's not true. It's just that because the improper integral had a value of pi over 4, that just tells us the improper integral converges. And that tells us the infinite series converges. So here's what I'd like you to do now. In the book, I'd like you to do a couple of problems. So I'd like you to go in the book. I would like you to do numbers 13 and 20. So pause the video, do 13, do 20. Once you've done those two, restart the video and I'll be here at the chalkboard working through the solutions. All right, number 13, you were asked, does the series n equals 2 to infinity n over natural log n? Does that series converge or does it diverge? And when I look at the structure n over natural log n, I'm having a bad feeling. I'm having a feeling, my gut feeling, if you will, is it's going to diverge. My gut feeling is it's going to diverge because of the nth term test for divergence. And that's because of the nature of n and natural log n. I know as you head off to infinity, I know n is heading to infinity, and I know natural log n is also heading to infinity. So we're heading to infinity, but natural log, it kind of takes a leisurely path to get to infinity. So I think this numerator is growing more rapidly than the denominator. So I don't have a good feeling that we're going to be heading to 0. But everything that I just babbled, I'm talking about the nth term test. So I'm talking about looking at the limit as n goes to infinity, n over the natural log n. Okay, I don't have any special magic algebra trick here. The only thing I can think of doing is saying, well, you know what? Let's look at the function of the reals, x over natural log x. I know this function of the reals and this function of the positive integers are identical for all the positive integers. So whatever the behavior of this function is, that the function of the positive integers has the exact same behavior. It's along for the ride. So I can quickly get the limit as x goes to infinity of x over the natural log x. I mean, it has the form infinity over infinity, so let's take it to the hospital. So that gives me a 1 over x. That's the limit as x goes to 1 over x is just x. Yep, that limit is infinity. Because this limit is infinity, we know that the function of positive integers, n over natural log n, has the same limit. And infinity is most definitely not equal to 0, so the series n over natural log n, it diverges thanks to the nth term test. Alright, so number 20. Let's see, when I look at number 20, I don't have much of a gut feeling on what's happening here. I see the numerator would be heading to infinity, the denominator would be heading to infinity. I think because the denominator has an e to, the exponent here is a 2n, and that's just an n, the denominator might be heading to infinity more rapidly than the numerator, but I don't have a feeling here on what the nth term test is going to tell me. So, I'm going to come over here to the side and I'm going to say, well, what about this function? What about that function on the interval 1 to infinity? It's positive on the interval 1 to infinity, and it's continuous on the interval 1 to infinity. And to show that it's decreasing on the interval 1 to infinity, I would get the derivative. I would let the derivative and the fact the derivative is negative tell me that the function's decreasing. So wait, it's positive, continuous, decreasing, sounds like a candidate for the integral test, which I initially thought was a good idea here because I think that's something that I would consider to be easy to integrate. In other words, let's look at integrating e to the x over 1 plus e to the 2x dx. Now notice I rewrote e to the 2x as e to the x quantity squared. See what the antiderivative will be? I mean, if you do a real quick quick U-substitution. If you let u equal e to the x, then du is e to the x dx. I mean, you're going to get the integral 1 plus u squared, 1 over 1 plus u squared du. That's inverse tangent. So the antiderivative of this, very quickly, let me get my limit as b goes to infinity in here, is inverse tangent of e to the x. And we need to evaluate that from 1 to b. Yeah, I kind of skipped the step of rewriting this as the limit as b goes to infinity, the integral 1 to b, e to the x over 1 plus e to the x squared. So let's try to get this limit. Well, let's see, limit as b goes to infinity. See, this is inverse tangent of e to the b minus inverse tangent of e to the first power. So that's just inverse tangent of e. I don't know what inverse tangent of e is, but I do know this. As b goes to infinity, e to the b is heading to infinity. And thanks to the graph of inverse tangent, I know this limit is pi over 2. So this limit is pi over 2 minus inverse tangent of e. Again, I don't know what inverse tangent of e is. It's just some number. But the limit exists. So that told us that our improper integral converges. And if the improper integral converges, that tells us that our infinite series converges thanks to the integral test. All right, so that's number 13, that's number 20. Hopefully you got those. I'm going to head back to the slides and see what's next. All right, folks. Hopefully you made sense out of that example. It's nice to see, inverse tangent coming back. Hopefully you did well on numbers 13 and 20. So let's continue on. So far in this section, we've added 2 more weapons in determining convergence, divergence of series. This next weapon is for a special family of series called p-series. But first, what we need to do is we need to define what a p-series looks like. So here's the definition of p-series. A series of the form, the sum n equals 1 to infinity, of 1 over n to the p, and I wrote out the first 3 terms of what a series like that would look like. 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus yada, yada, yada. A series of that form is called a p-series, where that p that you see in the exponent position is a positive constant. Note that if p has the value of 1, we have the familiar harmonic series. Sum of n equals 1 to infinity of 1 over n. So now that we know what a p-series looks like, let's look at this theorem. The p-series, the sum of n equals 1 to infinity of 1 over n to the p. The p-series converges if p is greater than 1. The p-series diverges if 0 is less than p is less than or equal to 1. Very easy to know when a p-series converges or diverges. A very, very friendly test. And before we take a look at some examples, you know what, I'd like to I'm going to simply outline the proof of that last theorem. I'm not going to crank through it, just outline it. So first off, if p is less than or equal to 0, then the limit as n goes to infinity of 1 over n to the p would not be equal to 0. And the series would diverge via, the nth term test for divergence. If p is equal to 1, we have the harmonic series. We know that diverges. So for the case where p is greater than 1, you would let f of x equal 1 over x to the p, and you would use the integral test. That's something that that I want to say we talked about when we were looking at improper integrals. But that's just outlining the proof. So here we go with an example. Going to have a lot of parts to this example. There they are. Make sure you write each one of them down. Get them in your notes, because I'm going to be heading off to the chalkboard to do each one of them. All right, now that we've learned about p-series, and that's a very easy to recognize a p-series, and it's a very easy test to know if it converges or diverges. This example had 4 parts, so let's knock them out one at a time. And we saw this one earlier in the section when all we knew was the nth term test for divergence. And remember, at that time we just said, it may or may not converge. Now we know it converges. Here's what I would write down. This is the reasoning. This is what I'd want to see. You look at this and you just say quickly, you write down, it's a p-series. P has a value of 2, which is greater than 1. So it converges. It's a convergent p-series. So if you wanted to, you could say converges via the p-series test. Very friendly. Now B. Going to do a lot of babbling here about B, but it's something really important to get under control. Technically speaking, our p-series and our p-series test tells us what's happening for the series from n equals 1 to infinity, 1 over n to the 1.003. This has a starting value at 4. So here's what's really important about this. By the way, you know this is a p-series. You know p is 1.003, which is greater than 1. So you know this converges. So what I need you to remember is the original series, it also converges, because what's the only difference between this series that starts at 1 and the series that starts at 4? It's just 3 terms. This series has 3 more terms at the beginning of it than this series. Please remember, the overall convergence or divergence of a series is not dependent on the first few terms. The first few terms mean nothing on the grand scheme of things. So this series, because it doesn't matter about those first few terms, it converges. And if you told me it converges because it's a p-series, p is equal to 1.003, which is greater than 1, I would be okay with that. I just wanted to highlight stuff that's really, really technical. And to hammer home one more time, the first few terms of a series doesn't mean anything. Okay, C. Well, look at that. N equals 1 to infinity. 1 over n to the 1/3 power. That's a p-series. P is 1/3, which is less than 1. That means it diverges. Very quick. Boom. We know it diverges. D. Now I'm going to babble a little bit more about D here. And this is also kind of important. First off, let me rewrite the series. It's 4 times 1 over n cubed. Okay, we know the series 1 over n cubed. We know that's a p-series. P is equal to 3, which is greater than 1. So it converges. See, there's a 4 in here. Our p-series isn't, our definition of a p-series isn't any number over n to the p. It's 1 over n to the p. So we know the series 1 over n cubed. We know that series converges. Taking a known convergent series, like 1 over n cubed, and multiplying it by a constant does not change the convergence or divergence. It doesn't change it at all. So since we know this series converges, that tells us the series 4 over n cubed converges because it's simply a constant times a known convergent p-series. The same thing is true about a divergent series. If you take a known divergent series and multiply it by a non-zero constant, it's going to diverge. So look at the harmonic series, the series 1 over n. We know it diverges because it's the harmonic series. We already determined it diverges. Because I know 1 over n diverges, I know the series 5 over n diverges. Because the series 5 over n is just simply 5 times the known divergent harmonic series. So please remember that. So there's an example. Okay, I'm going to do something kind of different here. Folks, I have about 8 problems I would like you to do. And then, restart the video to watch them. So there's going to be a total of 8. I'm not going to put all 8 of them up here right now. Let's start with number 25. So like I said, I'm going to have a total of 8. I mean, I'll write down all 8 if, we're going to look at these 8. 25, 27, 29, 35, 49, 53, 57, and 63. But I'm not going to do them all at once. So what I'm going to say right now is, I'm going to ask you to pause the video and just do number 25. And after you do that, restart the video. I'll be here at the board cranking through number 25. All right, here we go, number 25. It's the series n equals 1 to infinity, n cubed over e raised to the power of n to the 4th. Okay, immediately my gut feeling is, well, as n goes to infinity, n cubed over e raised to the n to the 4th power, those terms are approaching 0. I bet they're approaching 0 rapidly too, because that denominator is the exponential function e raised to an n to the 4th power. So my gut feeling is this beastie converges, but I have to do some work. The next thing that pops out to me is, well, if I had the function of the real variables, f of x equals x cubed over e x to the 4th, and I look at this function on the interval 1 to infinity, here's what I would find. It's positive. It's continuous. And computing the derivative would tell me that it's decreasing, which means I could crank it through the integral test. And I was thinking the integral test because I think this is something that's easy to integrate. I think, let me write it down. I think that's pretty easy to integrate if I do a U-substitution. If I let U equal x to the fourth, du is a 4x cubed dx. So when I substitute in, I have, I'll leave off my limits here. The denominator is e to the u, x cubed dx. Well, that's a 1/4 du. And see, I look at this as being 1/4 the integral e to the negative u du. That is easy to integrate. The antiderivative of e to the negative u gives us a negative 1/4 e to the negative u. So this was easy to integrate. So since I have my antiderivative, let me resubstitute to get negative e to the negative x to the fourth over 4. Evaluate that from 1 to b. So we get, oh, look at this. The limit as b goes to infinity, negative e to the negative b to the fourth over 4 minus negative, that's plus, e, okay, I put 1 in here, 1 to the fourth is 1, so I have e to the negative 1 over 4. All right, pulling this right up here, you're going to see I'm going to do a little rewrite. I'm going to rewrite this first term. I'm going to take e to the negative b to the fourth and drop it to the denominator. So I have negative 1 over 4e b to the fourth, and then plus a 1 over 4e. I decided to get rid of that negative exponent as well. So the limit as b goes to infinity of this first term, that denominator is getting incredibly large. Because it's getting incredibly large, the limit as b goes to infinity of the first term is 0. This is a constant. The limit of a constant is that constant. So the limit ends up being 1 over 4e. What does that tell us? That tells us the improper integral converges, which tells us our infinite series converges thanks to the integral test. All right, so next, I'm going to have you pause the video and do number 27. So pause the video, do number 27. Once you do 27, restart the video. I'll be here at the board cranking through the solution. All right, 27. You're asked to find or determine if the series n equals 1 to infinity n to the 1 over n, if that series converges or diverges. And see, I'm not looking at that and I'm not thinking that's something that's easy to integrate. It's not a geometric series. It's not a piece series. In fact, when I look at doing the limit as n goes to infinity of n to the 1 over n, well, I know that's the form infinity to the 0. I don't even know what that is. That's an indeterminate form. But that might be a place to start. In other words, let's look at the function f of x equals x raised to the 1 over x. Let's try to find the limit as x goes to infinity of x to the 1 over x. I think I did this limit back in Calc 1, but we're going to go through it again. Okay, the trick in doing this limit is you have to say, I don't know what it is. I'm going to assume the limit exists, and I'm just going to call it y. So that allows me to write y equals, the limit as x goes to infinity, x to the 1 over x. Then the key was to take the natural log of both sides of this equation. So you have the natural log of y equals the natural log, the limit as x goes to infinity of x to the 1 over x. And remember, because natural log is continuous, we have that property of limits that allows us to pass natural log through the limit process. Okay. Oh, then we have a property of logarithms. This is kind of cool. We have a property of logarithms that allows us to take the 1 over x and move it out front of the log statement. But here's the problem. Right now, as x goes to infinity, 1 over x is 0. The natural log of x is, well, as x goes to infinity, it's infinity. So the form of this, it has the form of 0 times infinity. Can't go to the hospital. But if I rewrite this, 1 over x times natural log x, if I just rewrite it as natural log x over x, multiply them together, now I have the form infinity over infinity, so we can go to the hospital. And remember, we're only going to the hospital on the right side. So the derivative of ln x is 1 over x. Derivative of x is 1, so we have 1 over x over 1. That's 1 over x. And we can do the limit now. Natural log of y, the limit as x goes to infinity of 1 over x is 0. That tells us y equals e to the 0, which is equal to 1. That means the limit as n goes to infinity of n to 1 over n is also 1. Remember, function of the reals, function of positive integers, same behavior as long as they agree for all the positive integers. We just computed the limit of the reals. We get this limit for free. And because this is not equal to 0, we know our series diverges thanks to the nth term test for divergence. So that's it for number 27. Next, how about doing 29 and 35? So pause the video, do number 29, then do number 35, restart the video, and I'll be here at the board to crank through the solutions. All right, folks, after looking at 25 and 27, somewhat involved. Hopefully you looked at number 29 and said, oh wow, how friendly. I mean, look, this is a p-series. P is equal to 10, which is greater than 1. The series converges. Boom, that's it. We just answered it like that. Now number 35, all right, the sum from n equals 1 to infinity of the quantity n over n plus 10, all of that junk raised to the nth power. Well, you have an n over n plus 10, all that raised to the nth power. Right now, I'm thinking of a limit. It has the form infinity over infinity, all that stuff raised to the infinity. I mean, who knows what that is? So let me show you a trick. It's just a little algebra trick. N over n plus 10. Making use of an old rule of exponents, n over n plus 10 is the same thing as n plus 10 over n to the negative first power. Which means n over n plus 10 to the nth power, I can think of that as n plus 10 over n to the negative first, and then all of that raised to the nth power. So look at where that's going to take me. I'm going to try to analyze this limit. I'm basically checking it for the nth term test for divergence. Alright, so n over n plus 10 to the nth power. I have that we can rewrite n over n plus 10 to the nth power as this. But I'm going to do one more step. There's another rule of exponents that says I can multiply these two exponents together to give me n plus 10 over n to the negative n power. Now I want to get rid of that negative exponent. So I can rewrite that as 1 over n plus 10 over n to the nth power. And then, okay, I'm starting to, excuse me, see some light at the end of the tunnel. Inside the parentheses, n plus 10 over n. Well, I could rewrite that as n over n plus 10 over n. N over n is 1 plus 10 over n. I immediately know what this limit is. I immediately know this limit is 1 over e to the 10th. Because I kind of remember doing these problems in the past. I remember doing a bunch of them in Calc 1, and I remember we did some, this semester. That you know the limit as n goes to infinity of 1 plus 1 over n to the n is e. You can replace this 1 with any non-zero number. I mean, let's just think of positives because we're dealing with sequence and series now. If this is a 3, then the limit would be e cubed. If it's a 5, the limit's e to the 5th. Those of you that suffered through my Calc 1, I had you do this as an extra, little mini assignment and then kind of prove the rule that you came up with. So this isn't anything new. But look at what we've analyzed. 1 over e to the 10th. That doesn't equal 0. Because it doesn't equal 0, that tells me that the series n over n plus 10 to the nth power, it diverges thanks to the nth term test. So folks, this trick was kind of important. We're going to see, coming up in the future, that sometimes we want to flip the numerator and denominator. And one way of flipping the numerator and denominator is to introduce a negative exponent. So that's why I thought I would show you the trick, and that's why I thought 35 was a good one to do. All right, so now, why don't you pause the video and do 49 and 53. After you do 49 and 53, restart the video. I'll be here at the board cranking through. All right, number 49. Does series n equals 2 to infinity 1 over e to the n, does it converge or does it diverge? I do know the general terms are approaching 0. 1 over e to the n. If I look at the limit as n goes to infinity of 1 over e to the n, that limit is 0. And actually, I think the terms are approaching 0, rapidly. So my gut feeling is this series converges because the terms of the series are approaching 0 and they're approaching 0 rapidly. Check out the series though. One little step, one little rule of algebra. 1 over e to the n, thanks to a property of exponents, you can rewrite that as 1 over e, that quantity, to the nth power. It's just an old rule of exponents. And once I rewrite it like that, I say, haha, that's a geometric series. R is equal to 1 over e. And 1 over e is most definitely less than 1. It converges. 53. So when I look at 53, my gut feeling is it diverges. And here's where I'm thinking. Here's how I'm analyzing it. Look at the denominator here. You have the square root of n squared plus 1. As n heads off to infinity, so as n gets incredibly large, this plus 1 is really doing nothing. So as n gets incredibly large, this fraction is basically the same thing as n over the square root of n squared. And for positive numbers, we know square root of n squared is n. So this fraction is basically n over n, which is 1. I'm thinking that limit is 1. I think it's going to diverge because of the nth term test. Now, because I think it's going to diverge because of the nth term test, I might as well try it. I might as well look at the limit as n goes to infinity of n over the square root of n squared plus 1. All right, so here's what separates us from the lower life forms. I can't just do that number sense argument that I just talked about. I need to have an algebraic way of doing this limit, or to figure out this limit. And here's the algebraic way. I'm going to divide numerator and denominator by n. I'm going to divide the numerator by n, and I'm going to divide the denominator by n. Notice when I divide the denominator by n, I've disguised the n as square root of n squared. And I know that's a positive n because we're talking about positive numbers, so I don't have to worry about any absolute values or plus or minuses. But check it out. That gives us, well, the numerator, n divided by n is 1. So the denominator, you have the square root of n squared plus 1 divided by the square root of n squared, which square root of n squared plus 1 over square root of n squared, thanks to a property of radicals, I can write that as the square root of n squared plus 1 over n squared. Then under the radical, I can simplify, n squared over n squared, that's 1, plus 1 over n squared. And I can do the limit now. Limit as n goes to infinity of 1 is 1. Limit as n goes to infinity of 1 is 1. Limit as n goes to infinity, 1 over n squared is 0. I get the limit to be 1. That is not 0. So our conclusion, this series diverges thanks to the nth term test. All right, so hopefully you got both of these. Final two, 57 and 63. So go ahead now, pause the video, do 57 and do 63. Once you've done 57 and 63, you know the drill. Restart the video. I'll be here at the chalkboard to work through the solutions. All right, here number 57, you're asked, is the series of n equals 1 to infinity 5/6 to the negative n? Does that converge? Does it diverge? Well, this is pretty friendly now that we know the power of negative exponents. In fact, 5/6 to the negative n, I can think of that as 5/6 to the negative first raised to the nth power. And then based on that last one we just did, 5/6 to the negative first, well, 5/6 to the negative first, that's the same thing as 6 over 5. So 5/6 to the negative n is really the same thing as 6/5 to the n power, which this is now very friendly. Just needed some algebra, rules of exponents, to rewrite it so we can see it's a geometric series. R is 6/5, which is greater than 1. Diverges. All right, so very friendly. 63. Again, 63, just a little bit of an algebra trick here. I mean, you're seeing a lot of these algebra tricks are just the old rules of exponents. I mean, 3 to the n plus 2, that's the same thing as taking 3 to the n and multiplying it by 3 squared. Because when the bases are the same and you multiply, you would add the exponents. Well, we know what 3 squared is. 3 squared is 9. And then we're left with this 3 to the n over 5 to the n, which there's an old rule of exponents that says 3 to the n over 5 to the n. You can write that as 3/5 to the n. And what do we have? We have a geometric series where r is 3/5, which is less than 1, which means that it converges. All right, so those were 8 homework problems that we just cranked through. Hopefully you did them and tried them before you watched the solutions at the board, and hopefully you're starting to get a little bit more comfortable with this and getting a feel for it. But there's one more topic that we're going to look at in this section. It's a topic that I find to be really cool. So let's head off to the slides and see what's next. All right. Hopefully that example made sense. And, I know I asked you to do a lot of problems, but they were some of your homework problems. I asked you to do a lot of them, and you started to see how everything was kind of playing the game. And that's one of the tasks involved. I mentioned this, in a previous video. Recognition is key. Recognition is important. Being able to look at a series and figure out how to attack it. So that's why I decided to have you do so many of your exercises at this time. So continuing on, we're going to conclude this section with something that I think is really cool. How we can estimate the sum of a convergent series, as long as it has positive terms, and bound the estimation. So just going to try to develop the concept a little bit here. So f is a positive continuous decreasing function on 1 to infinity. A sub n equals f of n. Kind of looking like the preamble to the integral test a little bit. If the series n equals 1 to infinity of a sub n converges to s, that is, the series equals s, then this thing called a remainder, r sub n, equals s minus s sub n. Okay, here, think s sub n, way back to when we did, partial sums. S sub n is just the sum of the first n terms of the series. So s minus s sub n, is the actual sum of the series minus the sum of the first n terms. That's what we're calling the remainder, r sub n. That remainder, r sub n, is bounded by, 0 is less than r sub n is less than the improper integral, n to infinity, f of x dx. Let's look at another way we can write this, and I'll go line by line here. So 0 less than r sub n less than the integral n to infinity f of x dx. Well, r sub n is s minus s sub n, so I can just substitute s minus s sub n in for the r sub n. And then I can add s sub n to each piece of that compound inequality to get s sub n less than s sub n plus the integral from n to infinity f of x dx. And remember, s sub n is the sum from n equals 1 to big N of a sub n. It's the sum of the first n terms. S is the actual sum of the series, the sum from n equals 1 to infinity of a sub n. And then we have less than, okay, there's an s sub n again, and the improper integral. If you look in the book on page 678, middle of the page, there's an inequality statement marked number 2, and it looks something like this. Okay, based on our previous slide, I'm going to rewrite that as, and I'll go through line by line, that r sub n we know is s minus s sub n. So that's the second compound inequality statement, just substituting s minus s sub n for r sub n. Add s sub n to each compound inequality. And then, well, s sub n is the sum n equals 1 to n of a sub n. And then we have plus the improper integral n plus 1 to infinity f of x dx. S, well, that's the actual sum of the series. And there's another s sub n. You know, the nth partial sum. So if you look at that, there's some neat things here. The sum from n equals 1 to n, a sub n, that's the nth partial sum, plus the integral from n plus 1 to infinity, f of x dx, that's called the lower bound, L sub n. And then the sum n equals 1 to n, a sub n, the nth partial sum, plus the integral from n to infinity, f of x dx, that's called the upper bound, u sub n. So in that compound inequality, that last compound inequality, the leftmost piece is the lower bound, the rightmost piece is the upper bound, and what's in the middle? That's the actual sum of the series. So that means that last compound inequality can condense to lower bound less than sum less than an upper bound. And I'm going to do one example of this. I think I've only assigned one homework problem where you're going to, go through this stuff. So what I'm going to do is I'm going to follow the directions in the text for exercises 41 to 44, and I'm going to use those directions on the following convergence series. Series n equals 1 to infinity, 1 over n to the 8th. I know that's a convergence series because it's a p series. P is equal to 8, which is greater than 1, so I know it converges. So I'm going to work this example out on the board. So here we go to the chalkboard. All right, folks. The series 1 from n equals 1 to infinity, 1 over n to the 8th, I know it converges. It's a p series. P is 8, which is greater than 1, so it converges. And we're going to crank through the directions for exercises 41 to 44 to see something really cool about everything that we just saw, on the previous slide. So when I read the directions for 41 through 44, Part A says find an upper bound for the remainder in terms of n. Well, that remainder is bounded by the integral n to infinity 1 over x to the 8th dx. That's what it's bounded by. So to determine actually what this is, let me come over here to the side. And to do that, Well, I'd look at the limit as b goes to infinity. The integral from n to b, 1 over x to the 8th dx. I rewrote 1 over x to the 8th as x to the negative 8. We can get an antiderivative. So the antiderivative of x to the negative 8th, that's negative 1 over 7x to the 7th. And we had to be negative 1/7 x to the negative 7th. I'm just rewriting it like this. And then, well, we have the limit as b goes to infinity. Negative 1 over 7b to the 7th minus negative, so that's a plus, 1 over 7n to the 7th. So as b goes to infinity, this would be 0. This is a constant. So the remainder is bounded by this, and we just evaluated that this equals 1 over 7n to the 7th. Okay, now let me look at part B. Part B, find how many terms are needed to ensure that the remainder is less than 10 to the negative third power. All right. How many terms do we have to add up to ensure that the remainder is less than 10 to the negative third power? Well, folks, that's the bound on our remainder. So in part B, you're basically being asked to solve 1 over 7n to the 7th is less than, well, they said 10 to the negative third. You can rewrite this as 1 over 1,000. And then multiply both sides by least common denominator. And then you have to divide by 7. And then you'll have to take a 7th root. You do all that correctly, you're going to get n is greater than 2.0316, blah, blah, blah. But remember, n is talking about, we're talking about positive integers. So if it's greater than 2.03 whatever, that means we need 3 terms, because that's the positive integer that's greater than 2.03. So that means we need 3 terms. All right, so let's look at part C. Part C. Find the lower and upper bounds, L sub n and U sub n respectively, on the exact value of the series. Okay. So the lower bounds and upper bounds. Okay, I'm going to erase this. So let's see, the lower bound. Well, that lower bound that we just saw on the slides, the lower bound is equal to, well, the sum of n equals 1 to infinity. I'm sorry, n equals 1 to big N of a sub n plus the integral n plus 1 to infinity 1 over x to the 8th dx. All right, folks, we just integrated from n to infinity 1 over x to the 8th dx. So you can look at what we did. It's the same process, and you're going to end up seeing that this improper integral here has the value of 1 over 7 n plus 1 to the 7th power. I mean, it looks very similar to this. It should, because, I mean, it's just the lower limit of integration is just shifted by 1. Big deal. Remember this here is the nth partial sum. It's the sum of the first n terms. So we now have an expression for the lower bound. An expression for the upper bound, that U sub n. Remember, that's the sum n equals 1 to n a sub n plus the integral n to infinity 1 over x to the 8th dx, which, okay, that's the nth partial sum plus the 1 over 7n to the 7th. So that's our upper bound. So here's what's kind of cool. Part D, at least I hope. Part D. Find an interval in which the value of the series must lie if you approximate it using 10 terms of the series. So we're going to approximate the sum of the series by just adding up the first 10 terms of the series. We're going to find just the sum of the first 10 terms. Okay, now I'll let you do that. I'll let you do 1 plus 1 over 2 to the 8th plus 1 over 3 to the 8th plus 1 over 4 to the 8th, the first 10 terms. When I do that and I use my calculator, I get 1.004077346. That's using the first 10 terms to approximate the sum. I can come up with a lower bound. Here's my lower bound. My lower bound is the sum of the first 10 terms. So let me write this down. L sub 10 is the sum of the first 10 terms plus 1 over 7, and 10 goes in here. That's the lower bound. The upper bound, U sub 10, is the sum of the first 10 terms plus 1 over 7 times 10 to the 7th. Okay, running out of room, so I'm going to erase this. So if you use your calculator, you can get, you're going to take this, that's S sub 10, plus that, 1 over 7 times 11 to the 7th power. You can get the same thing for the upper bound, S sub 10 plus 1 over 7 times 10 to the 7th power. And you're going to get the lower bound and the upper bound to both be the same thing as S sub 10. In other words, your lower bound is 1.004077353. The upper bound is 1.004077353. And we know the actual sum of the series. It was the last line I wrote on the slide before we came here to the board to do this. We know the actual sum of the series is trapped between the lower bound and the upper bound. So here's what I think is really cool, really amazing. We just added up the first 10 terms of this series. We added up the first 10 terms, and this is what we got as the sum of the first 10 terms. And the lower bound and the upper bound, for just adding up the first 10 terms, the lower bound and upper bound happened to be the sum of just adding up the first 10 terms. So while I don't know exactly what the sum of this convergence series is, I don't know exactly, I feel pretty comfortable saying that it's pretty close to 1.004077346. I mean, that, to me, that's astonishing. All right, so I think I only have you doing one problem like this. I do, number 41. The rest is getting familiar and comfortable with the nth term test for divergence, the integral test, and P-series. So you're ready to go do the homework. So go ahead and do the homework here in section 10.4, and thanks for watching.